Okay, section 4 deals with something we call permutations and combinations. So to this point, we've used the multiplication principle. Well, actually, let's back up. We used Venn diagrams to try to figure out how many objects are in satisfy a particular category. Here, when we started using the multiplication principles, we did not actually list out all the different possible things that could happen. The numbers are just too huge. And the thing I will be talking about in this section and the next section, and especially in chapter 7 with probabilities there, the idea of a permutation is that order is extremely important. Combinations, the order is not important. And we're assuming that repetitions are not allowed. Remember the horse races. The horse race. We had 5 horses, and if you bet A, B, C, and in fact it was A, C, B, first, second, and third, you lost the bet. The order is extremely, extremely important. We also want to remind you that you're not allowed to have repetitions. That's a no-no. And that makes sense from the horse racing point of view, or if I'm displaying a bunch of Rembrandts, you don't have the same painting in this slot and this slot. That doesn't make any sense. And here we have an example of an art. So the art department received a gift of 7 paintings from an alumnus artist. An art major is to select 3 of the paintings and arrange them in 3 specific locations in the foyer of the art building. How many ways can this be done? Notice it says specific locations. That is telling me the order is very, very important. If you were to go to the Louvre in France, and right there are going to be positions in that art museum that are very, very important. Then as you go towards the back, they're not quite as important as those that are on display. So we have 7 paintings, and we can only display 3 of them, and the locations are very, very, very specific. That is telling us that the order is very important. And this is something you're going to have to pay attention to when you're doing this, whether is it a permutation or a combination. Permutation is order is important. There's special displays. Think about you've got a Picasso, a Rembrandt, and an Areola. Obviously, my painting or drawing is not going to supersede this guy, so the order is very important. So we could use the multiplication principle. It's the same thing. First place, second place, third place. So I have 7 paintings that can go in the first. I pull one of them out. I'm not telling you which one I'm pulling out. I have 6 paintings left. I pull one of them out. I have 5 paintings left. So multiplication principle just says 7 times 6 times 5, 30 times 7 is 210. So when we're talking about permutation, it's an arrangement of objects. Repetitions are not allowed. Obviously, you don't have the Rembrandt and the same Rembrandt in 2 different places. And the order in which the objects are selected, arranged, is important. That's what we mean by a permutation. Let's take another example. How many different ways can a penny, a nickel, a dime, and a quarter be given to 4 children if one is given to each child? Now, is this important? Is order important? Not important. Notice there's a distinction of the objects, right? And we have 4 children. Obviously, we don't have 2 of the same. They're all different people. So definitely some order has got to be important here, because if you can give, for example, Mary, you can give her a quarter or you can give her a penny. Those are two different situations. So what we do is it's the same idea. Each child may be considered a position. Order is important. Obviously, Alice Fred is not the same as Fred Alice. So we have what? Child number 1. There are 4, not just 4. This could have been 7 coins given out to 1 each. So child number 1 gets 1 out of the 4. There are only 3 left, then only 2 left, then only 1 left. That is your multiplication principle, and you can't drag that out any further. In other words, it's 24 ways of doing this. At the Cumberland River Festival, 4 young women are stationed at the historic Fort House. 1 woman stands at the entrance, 1 in the living room, 1 in the dining room, and 1 in the back on the back veranda. So if you think about this, if you've ever gone to someplace like Colonial Williamsburg or some other historic site where they have interpreters, when you say 4 women, they're all different, right? And notice that there is a distinction in where they are standing. The entrance, dining room, living room, dining room, and the veranda. So there is a definite distinction between the locations and the people. So let's say that we have 10 women available. All right, so I need what? 4 out of the 10. And the reason for 4 is entrance, living room, dining room, and the back veranda. So order is important. Alice on the veranda, let's compare it to Alice in the dining room, are 2 different things. It's the multiplication principle again. It's the same old thing. So you have 10 women that are available. You pick 1 out. So you're going to put 1 of the 10 at the entrance. You only have 9 left. 8 left and 7. So you just multiply all those guys together. All right, now notice these numbers are getting bigger and bigger and bigger because we're multiplying a lot of numbers. So notation. We come up with something called the factorial function. And when I write down 13 exclamation point, it doesn't mean 13 is excited, okay? It is a shorthand notation for 13 times 12 times 11 times 10, all the way down to 3 times 2 times 1. And notice what's happening is you're multiplying a bunch of numbers together, just like you're multiplying a bunch of numbers and you're going down by 1. So 5 factorial is a shorthand notation for 5 times 4 times 3 times 2 times 1. By definition, now throughout the semester I will always explain why something happens. This, I'm not going to do that. So 0 factorial is going to be by definition 1. So what we're going to do is we're going to start expressing these big numbers here in terms of the factorial functions. Okay. Suppose I have 7 factorial divided by 5 factorial. Now DDT subscript 1 means don't do this, okay? So you could take 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 5 times 4 times 3, and then you cancel out, correct? DDT subscript 2 means do this. I want you to notice that eventually what happened was the 5, 4, etc., those all canceled, correct? So instead of writing this as 7 times 6 times 5 times 4, I'm just going to take the 5 factorial and peel it off. The reason for that is if I take the 7 times 6 and then stop it at 5 factorial, I can immediately cancel the 5 factorials. Okay? So what you're going to do is you're going to take the numerator, you're going to stop it at where the denominator is at, and then you're going to do your cancellation. That's much, much quicker than... So, 13 factorial over 10 factorial. What am I going to do? I'm not going to take 10 and write it all out. And I'm not going to take 13 and write it all out. I'm going to stop the 13 at 11. And I'm going to peel off the 10 factorial. So if I do that, the 10 factorials are going to cancel, so I get a whole bunch of cancellations without having to write everything out. So you're going to leave this alone, you're going to leave this alone, you're going to stop it here at 13, 12, and 11. Cancel, and you're left with 13 times 12 times 11. And now I can easily calculate that. Notice that the example here, this is saying I have 13 horses. And I could have one of those horses come in first, one of the 12 coming in second, and one. So notice that this number can be written as this guy. And that's going to be very important when we calculate, when we come up with the permutation formula. Now, what does 0 factorial mean? By definition, and I do not want to explain why, 0 factorial is defined to be 1. So we don't have any cancellations to worry about. 4 times 3 times 2 is 24. Let's take another example. Suppose I have this expression and I want to simplify it. Now, parentheses means you have to do what? Stuff that it's inside. So I take 8 minus 2, which is a 6, and I have to take the factorial. I have to do the 5 minus the 1 first, which is a 4 factorial. Now what do? We take the 6 and we stop it at the 5, and we have a 4 factorial left over. This is going to cancel with this one, and we're just left with 6 times 5, which is 30. So please don't take 6 times 5 times 4 times 3 times 2, and then 4, 3, 2, 1. Cancel. Just pull off a 4 factorial, and you're left with a smaller number that you don't have to be messing around with. Okay, now, let's go back to our 5 horses again. So, how many horses can come in first place? One of the 5, right? How many horses do we have left? 4. Then I have only 3 left in third place. Multiplication principle just says multiply those. Now what I'm going to do is I'm going to write it as a fraction. Notice a 5, a 4, and a 3. I'm going to make this, I'm going to multiply by 1 disguised as 2 times 1 over 2 times 1. Why am I doing that? Because then upstairs, so I'm not canceling, I'm actually putting in a 1 disguised as 2 times 1 over 2 times 1. And I want you to notice upstairs it is a 5 factorial, and downstairs it's a 2 factorial. Okay. So if I rewrite this again, so I'm not canceling. I'm trying to write it in what's called the permutation formula. So I have 5, 4, 3, 2, and 1. And I want you to notice that the number 2 times 1 could actually be 5 minus 3, which is 2 factorial. Let's think about this. I have 5 horses that come in first, 4 that come in second, 3 that come in third. So if I was to take the 5, 4, 3, 2, 1, that's a 5 factorial. And then if I took 5 minus 3, so we have what? 3 places out of 5 horses. 5 minus 3 is 2 factorial. In other words, I can write the number of ways things happen in terms of the number of places and the number of horses. Now 5, 4, 3, 2, 1, I'm going to call that 5 factorial. And 5 minus 3, which is the 2 factorial. but I'm going to leave it as 5 minus 3. This is our formula for our permutation. The permutation just says I have 5 horses, and I've got a first, second, and third. How many ways can this happen? P of 5 choose 3 is called, I'm choosing 3 objects out of 5 objects, and the P stands for permutation. And order is very important. Remember, ABC is not the same as ACB, right? Order is extremely important. That's how we define the permutation formula. So, the formula, and this is on your formula sheets, so you don't have to memorize anything. P n choose K is the permutation of choosing K objects out of n objects, and think of first place, second place, third place, etc. That's our permutation. So, what does this mean? P of 10 choose 4. Okay, I have 4 objects. I'm choosing them out of 10, and the permutation says order is very important. So, I've got 10 paintings, and I want to display 4 of them, and order is important. So how do we calculate that? We take how many things we have available. I'm choosing 4 out of the 10, which is going to be what? 6 factorial, correct? Please don't write this as 10 times 8 times 9, blah, blah, blah. Stop it where? At 6 factorial. So you're going to take the bottom and you're going to stop that. So 10 times 9 times 8 times, it's still going to be a big number, but it's a lot less than, again, please don't take the 10 times 9 times 8 times 7 times 6 times 5. Just stop it at the what? The 6 factorial in the denominator. And so we ended up with, what was that, 50,040. So, this is our horse racing problem again. I've got 5 horses, 3 places. 5 factorial divided by 5 minus 3 factorial. Do what's inside the parentheses. 2 factorial. Stop the top at 3. Cancel. You get the same answer. What does this mean? I have 7 places to display my paintings, and I want to choose 7 out of those. So what do I do? The number of places I have available is 7. The number of objects I'm going to choose is also 7. So we take the difference. Now remember, by definition, 0 factorial is, by definition, 1. Which is going to be a huge number. And personally, I don't care what that number is, but we just have to... Okay, another example. We have 8 members of a committee, and I need to form an administrative committee consist of a chair, vice chair, secretary, and treasurer. How many ways can we do this? Now, first question, is the order in which you pick people, is it important? Yeah, the chair position is not the same as a secretary. The vice chair is not the same as a treasurer. These all have different significant attributes to them. So that means you are going to, this is the permutation. Order is important. So you could do the following. You have now 4 places, right? You've got chair, vice chair, secretary, treasurer. You could do this by multiplication principle, correct? So you had, what was it, 10 I think it was? Well, 8 I guess. Too many pages here, sorry. Excuse me, so you have 8 people available. So that means you have 8 positions available. You're choosing 4 out of the 8. So our permutation formula says 8 factorial, 8 minus 4 factorial, which is 4 factorial. Please do not go 8 times 5 all the way down. Stop the 8 at 5. Cancel, and you get 1680. Now I want you to notice that that's the same. If you look at this calculation right here, that's the same as 8. It's a horse race again. 8 people, 7, 6, 5. It's the same thing. So when we were doing the multiplication principle and the order was important, we were actually using the permutation formula.